So this video is a problem session which is based on the material that was covered in the first 2 weeks of this course. The main intention of the problem session is to supplement the problems that have already been given in your assignments. So I hope that you have given a considerable amount of thought to the problems that were given in your assignments. So let's now look at a few more problems. Okay. So problem 1. So the problem 1 is as follows. Let V be the set of all elements x, y such that x, y are in R. Basically it is the Cartesian product of R with itself. Define vector addition in V component wise and scalar multiplication as follows. What is the scalar multiplication? The scalar multiplication is A times x, y is equal to x, 0 for all x, y in capital V and A in the field of scalars. So the problem is to check, is V a vector space with these operations. So notice that we are looking at the same set V, which is R2. The only thing is we are tweaking the vector addition. Actually vector addition is the same. The scalar multiplication has been tweaked to the new one which is underlined in green, and our task here in this problem is to check whether V is a vector space with these operations. Alright, so what do we need to do in order to establish this or solve this problem? So let's look at a solution. The first thing to notice is, first thing to check is whether V is closed under vector addition and scalar multiplication. So the vector addition, so recall the vector addition which is component wise, is given by x1 y1 plus x2 y2 is equal to x1 plus x2 component wise y1 plus y2, which is an element in capital V for all x1 y1 and x2 y2 in capital V. So this is something which we have already seen in the case in the example where we checked that R2 is a vector space, because the vector addition in this problem is the same as the vector addition there. So yes, V is closed under vector addition. How about scalar multiplication? So scalar multiplication. So let x, y be in R2, in V. V is the same as R2, but let me just call it V, because that is what the vector space is being called as. So let x, y be in V and C be an element from the field of scalars. Then C times the scalar multiplication. How is it defined? C times xy is x, 0, which is an element in capital V, right? It is after all an element in capital V which has the second coordinate 0. Recall that V is nothing but the set of all tuples x, y with xy in R, right? So yes, so this is also in V. So hence V is closed under both vector addition and scalar multiplication. We take two vectors and look at the vector addition of that gives you back a vector in okay. So if you take two elements in V and if you look at the addition component wise, it is giving back an element in V, and therefore it's closed under vector addition. And similarly, if you take any element x comma y in any scalar, look at the scalar multiplication as defined here, it is giving us back an element in capital V. And therefore, V is closed under vector addition and scalar multiplication. Okay, so what is now needed to be checked for these two operations? Properties 1 to 8 need to be checked. All the properties 1 to 8 listed in the definition of the vector space should be satisfied for V to be a vector space with these operations. So, let us now check the properties involved in the definition. So, let us now check for the properties 1 to 8 which is listed in the definition of the vector space. So, property 1. So, what was the first property? Property 1 dealt with whether this vector addition is commutative. So, let us take two elements in V. So, x1 y1 and x2 y2 be in capital V. What do we need to do? We need to check that if V1 and V2 are two vectors in capital V, two elements in capital V, V1 plus V2 should be the same as V2 plus V1. So, let us see what is x1 y1 plus x2 y2. x1 y1 plus x2 y2 is just component wise addition, which is x1 plus x2 y1 plus y2. And what is so notice that x1 plus x2 is just addition of two scalars. So, notice that x1 plus x2 is equal to x2 plus x1, and similarly y1 plus y2 is the same as y2 plus y1. Why is this the case? Because addition of scalars is commutative. Real numbers, if you add in whatever order you wish, the answer is going to be the same. That is the reason. So, let us call this star and call this observation star star. Then what is x2 y2 plus x1 y1? This again by component wise addition is just going to be x2 plus x1 comma y2 plus y1, just component wise addition. And by star star, this is equal to x1 plus x2 y1 plus y2, right. So, let me write this by star star here, by star star. And what is this? This is equal to x1 y1 plus x2 y2 by star above. So, basically what we have established is x2 y2 plus x1 y1 is the same as x1 y1 plus x2 y2, thereby establishing commutativity. So, yes, property 1 is satisfied. Property 1 is satisfied. Okay, now let us look at property 2. Property 2 dealt with associativity. So, if you take three vectors v1, v2, v3, the question of whether, if you look at v1 plus v2 plus v3, the question of whether v1 plus v2 is added first and then added to v3 shouldn't matter as compared to whether v1 is added to the vector addition of v2 and v3. So, for that we need to take three vectors v1, v2, v3, three elements v1, v2, v3. Elements here typically look like x1, y1, x2, y2 and x3, y3, v1, v2, v3, v elements in capital V. So, we are interested in what is x1, y1 plus x2, y2 plus x3, y3, whether this is the same as, we will come to that. So, this, if you notice, this is just equal to x1 plus x2, y1 plus y2 plus x3, y3. We added the first two vectors first, and now this is going to be equal to x1 plus x2 plus x3, y1 plus y2 plus y3. But what do we know about the sum of scalars, sum of real numbers? We know that that is a associative addition, right? So this is equal to x1 plus x2 plus x3. The order here doesn't matter, so we will make use of that to write it like this. But notice that this is nothing but x1 y1 plus x2 plus x3 comma y2 plus y3. And what is this? This is nothing but x1 y1 plus x2 y2 plus x3 y3. And that establishes that property 2 is satisfied. So hence property 2 is satisfied. So what was property 3? Property 3 talked about the additive identity, the existence of a 0 vector. So my claim is 0, 0 is the 0 vector for the vector addition. So in particular 0, 0 is an element of capital V. So if you look at x comma y plus 0, 0, what do we have? This is equal to x plus 0, y plus 0. But any number added to 0 should give you back the same number. So this is equal to xy. So any vector v added to the 0 vector is giving us back v. So yes, property 3 additive identity does exist. Property 3 is satisfied. How about property 4? Property 4 talked about additive inverse. Given any vector v, we would like to look for another vector w such that v plus w is the 0 vector, the 0 element. So this is property 4. Let's see if this is getting satisfied. Property 4 demands that let x, y be a vector, be an element in capital V. The addition is the same as the addition in the vector space R2. So we know what to expect. Then hence minus x minus y is a candidate, right? Then minus x comma minus y is an element of capital V, and x comma y plus minus x comma minus y is just x minus x, x plus minus x, which is x minus x, y plus minus x, which is y minus y, which is nothing but the 0 element. So yes, property 4 also is satisfied. Every vector v has an additive inverse. What was the fifth property? The fifth property is the existence of multiplicative identity. So property 5. So let's look at a vector v, which is say xy in capital V. So an element in capital V is being taken. We would like to check. So v be equal to this. So what was the multiplicative identity demanding? It was demanding that 1 times v is equal to v for all v in capital V, right? This is what we would like to check. But what is 1 times x comma y? So to do that, let's go and recollect what was the definition of the scalar multiplication, which I am now underlining in the green here. So any scalar c times x comma y is giving us back x comma 0, as you can see. So 1 times x comma y will give you back x comma 0. So it doesn't matter what c is, right? Every scalar should give you back the vector which is the first coordinate, and 0 is put in the second coordinate. So this is the definition, right? By definition, this is what it is. But if y is not equal to 0, then xy is not equal to x0, right? So this, however, if say x comma y is the vector 2 comma 3, let's say 3 not equal to 0, right? So 1 times 2 comma 3 here by definition is equal to 2 comma 0, which is not equal to 2 comma 3. We should have got 2 comma 3 if the property 5 is to be satisfied. So hence property 5 is not satisfied. It's not satisfied. So therefore V is not a vector space with these operations. So we have already solved the problem establishing that with these operations we cannot be a vector space because the multiplicative identity, the property involving the multiplicative identity is not getting satisfied. Well, out of curiosity we could ask what about the remaining properties. It doesn't matter because we have already established that V is not a vector space. However, just to satisfy our curiosity, let us look at the remaining properties as well. Property 6. Property 6 was about the multiplicative associativity, right? So if you look at AB times say x comma y, let me now do a quick observation. This is just going to be any vector any scalar times x comma y by the scalar multiplication is just going to be x comma 0, the first coordinate, and the 0 in the second coordinate. But we demand that this be equal to a times b of x comma y, right? And what is this? This is just a times x comma 0. B times x comma y is x comma 0, and a times x comma 0 will again be equal to x comma 0. So yes, this is equal. If you notice, this is equal. Therefore, property 6 is actually getting satisfied. So that is interesting. So even though property 5 is not satisfied, property 6 is still getting satisfied. How about property 7? Property 7 demands that a plus b times x comma y, let's see what this is. This is equal to, it doesn't matter what, a plus b, say c times xy is just going to be x comma 0. And what is a times x comma y plus b times x comma y? Oh, this was property 8, I guess. So let me just put it here. Property 8 satisfies, or rather whether it is satisfied or not, let's check. So this is going to be equal to x comma 0 plus x comma 0, which is actually equal to x plus x comma 0, which is 2x comma 0, right? So this is not necessarily, if x is say non-zero, then this is not going to get satisfied. So for example, look at 1 plus 1 on 1 comma 2. This by the first part will, or rather direct, so this is just 2 times, so let me not use the green, this is just 2 times 1 comma 2, which is equal to 1 comma 0 by the scalar multiplication. Any scalar times a vector will just give you the same coordinate in the first, so it's the same first coordinate, right? But what about 1 times 1 comma 2 plus 1 times 1 comma 2? This is just going to be equal to 1 0 plus 1 0, which is equal to 2 comma 0. This is not equal, as you can notice, and therefore property 8 is not getting satisfied. So we have one more property which is not getting satisfied. Not satisfied. Actually, let me not now bother about property 7, but let me just tell you that, or maybe I'll just write it. We need to check that a times x1 y1 plus x2 y2, this is equal to a times x1 plus x2 y1 plus y2, which is equal to x1 plus x2 comma 0. And what should this be equal to? This should be equal to a times x1 y1 plus a times x2 y2. But what is that? That is equal to x1 comma 0 plus x2 comma 0, which is equal to x1 plus x2 0, which actually are equal. and therefore property 7 is satisfied. So if you start worrying about all the properties, we will notice that the fifth property and the eighth property are not satisfied. So even if one of the properties are not satisfied, it cannot be a vector space. We just checked the remaining three properties out of curiosity, I would say. Alright, so we have completed the first problem and concluded that the set V with the vector space operations as defined in the problem cannot be a vector space. Okay, now let us look at the next problem, problem 2. Prove that the set W1, which is say x, y, z in R3 such that 2x plus 3y plus z is equal to 0 is a subspace of R3. However, W2, which is the set of all x, y, z in R3 such that 2x plus 3y plus z is equal to 1 is not a subspace of R3. So after looking through the solution, you will notice that 2x plus 3y plus z is equal to any non-zero number, not necessarily 1. You look at wk to be equal to x, y, z in R3 such that 2x plus 3y plus z is equal to k, that will not be a subspace. It has to be equal to 0, otherwise it will not be a subspace. The same proof will go through. So let us look at a solution. So this is more like a prove that, so let us call it a proof. So W1 is a subspace of R3, that is what we would like to prove here. But when does some subset become a subspace? If you recall the definition, it's going to be a subspace if in the borrowed vector space operations it is closed under both the operations. So enough to show to check that W1 is a subspace, enough to show that W1 is closed under the vector addition and scalar multiplication which is borrowed from capital V. So let us take two elements and look for whether vector addition of those two elements in W1 gives us back an element in W1. So let x1, y1, z1 and x2, y2, z2 be two vectors in W1. What does it mean to say that something is in W1? Let me go back and remind you what W1 is. W1 is the set of all x, y, z such that 2x plus 3y plus z is equal to 0. So this implies 2x1 plus 3y1 plus z1 is equal to 0, and this implies the fact that the x2, y2, z2 is in W1 implies that 2x2 plus 3y2 plus z2 is equal to the scalar 0. We would like to see what happens to x1, y1, z1 plus x2, y2, z2, whether this particular vector is in W. But what is the vector addition of this? This is component wise addition, if you recall. This is going to give you x1 plus x2, y1 plus y2, z1 plus z2. And let us see if this belongs to the set W1. But what is the requirement for this particular element to be in W1? It should satisfy the condition that 2x1 plus x2 plus 3y1 plus y2 plus z1 plus z2, this should be equal to 0 if at all this sum should be in W1. So then this is what will happen. Then this is equal to, let's write it out. This is 2x1 plus 2x2 plus 3y1 plus 3y2 plus z1 plus z2. Notice that all these are scalars. 2x1 is a real number, 2x2 is a real number, 3y1 is a real number, 3y2 is a real number, and so on. And the vector addition is commutative, and using that we can write this as 2x1 plus 3y1 plus z1 plus 2x2 plus 3y2 plus z2. Let's just go up. Notice that by whatever I am putting now as star, this is equal to 0 plus 0 by star, which is equal to 0, and therefore x1 y1 z1 plus x2 y2 z2 belongs to capital W by what we have just observed. So yes, W is closed under the vector addition which is borrowed from R3. How about scalar multiplication? We have already seen similar ideas. So let x, y, z be in capital W1 and C be in R. Then what is this? This is equal to Cx, Cy, Cz. And let's look at whether this vector in the right, Cx, Cy, Cz, does it belong to the vector space W. So we need to look for 2 times Cx plus 3 times Cy plus Cz is equal to 0, which is Cz. Is this equal to 0? That is the question. I'll just write it as C times 2x plus 3y plus z, but we know that 2x plus 3y plus z is 0 because x, y, z belongs to W1, and this is equal to C times 0, which is equal to 0. So yes, so this implies W1 is a subspace. Now what happens to W2? So I would say that W2, so let me do one thing. Let me note this part as maybe a star. So I'm going to use the star to conclude. So now is W2 a subspace? That is what we would like to answer, or rather we would like to prove that W2 is not a subspace. So in order to do that, we should show that it is not closed under either vector addition or the scalar multiplication. So let's take x1, y1 and z1 in W2 and x2, y2, z2 which is in W2. We would like to see if the vector addition is in W2, but we already checked this out, right? What is x1, y1 plus, x1, y1, z1 plus x2, y2, z2? This is just equal to x1 plus y1. Let me quickly write it. And we would like to see whether this belongs to W2. What is W2? Recall that W2 is defined in this manner. So I am underlining it in green. 2x plus 3y plus z, the sum of the coordinates with these linear combinations should be equal to 1. That is the requirement. So let's look at 2 times x1 plus x2 plus 3 times y1 plus y2 plus z1 plus z2. Now let me show you what was put in star. Yeah, so maybe this is what I would like to put in star. This tells us that this is equal to 2x1. Same argument tells us that this is equal to 2x1 plus 3y1 plus z1 plus 2x2 plus 3y2 plus z2. But what is 2x1 plus 3y1 plus z1? That is equal to 1 because x1, y1, z1 belongs to W1. Similarly, this is also equal to 1 and the sum of these two will give you 2. But what was our requirement? Our requirement was that this vector, if you look at 2 times the first coordinate plus 3 times the second coordinate plus the third coordinate, we should have got 1 for it to be in the vector subspace. Here we are getting 2 and therefore hence W2 is not. So this vector sum is not in W2. W2 is not closed under vector addition. So W2 is not a subspace and hence and therefore not a subspace. If you had taken scalar multiplication and checked, even that wouldn't have landed up here. It will give you something like C times 1, right? And therefore not a subspace. So even if one of the two conditions are not satisfied, it will not be a subspace. Alright, so we have proved or rather completed problem 2. Okay, so the next problem is in the vector space of all functions from a set to R. So let S be a subset of the real numbers and W be the set of all F in F of S comma R such that F of S naught is equal to 0 for a fixed X naught in capital S. So what is F of S comma R? Recall, I will come to that. So then prove that W is a subspace of F of S comma R. Okay, let us look at a solution to this problem, rather proof, because this is a prove that problem. So let us call it a proof. So what was F of S comma R? Recall that F of S comma R is the set of all functions from S to R. And what was the vector addition and scalar multiplication there? It was pointwise. So with vector addition, if you take two functions and if you look at F plus G, we would like to say that it is a function from S to R, right? So we will define what this is at a point S in capital S. This is just F of S plus G of S, which makes it into an honest function from S into R. And what about CF of S? We just, so for this is for F comma G in F of S comma R, and this is equal to C times F of S, where F is in capital F of S comma R and C is in, so this is the vector addition and scalar multiplication which we had defined during the lectures, and it was left as an exercise for you to check that this is indeed a vector space. So like in the first problem, you should have checked for whether it is closed under vector addition and scalar multiplication and seen what the properties 1 to 8, whether properties 1 to 8 are indeed getting satisfied. Yeah, in the process you would have had to guess what the additive identity is, what the inverse of a given function is, and so on. But they are all quite straightforward. Okay, so our goal here in this problem is to show that we are given a very particular subset. This is the set of all those functions f from S to R, where f satisfies the condition that f of S naught is equal to 0, where S naught is some fixed point. So if say S is the open interval 0, 1 and S naught is half, this will just turn out to be all functions from 0, 1 to R, so that f of half is equal to 0, one such example. Okay. Okay, so we will show that W is always a subspace. Again, like in the previous problem, we just have to show that W is closed under vector addition and scalar multiplication, but that is quite straightforward. So let f comma g be in capital W. This implies that f of S naught is 0 and g of s naught is 0. Okay, so now let's look at the vector addition of f plus g and look at what is the value at s naught. But by the definition, f plus g of s naught is equal to f of s naught plus g of s naught, which is equal to 0 plus 0, which is equal to 0. So therefore, which implies that f plus g belongs to capital W. How about scalar multiplication Cf times s naught? So this is for f g in W and C in R. This is what is getting satisfied. Cf at s naught is equal to C times f of s naught, but f is in capital W means that f of s naught is 0. This implies this is C times 0, which is equal to 0. Hence, Cf is in W. So W is closed under both vector addition and scalar multiplication. W is hence a subspace of f of s comma R. Next, let's do a problem which is similar to one of the assignment problems. Problem 4 demands that we check whether the first vector can be written down as a linear combination of the other two vectors. So check whether the first vector is a linear combination of the other two vectors in the following. The first one is minus 2, 2, 2, 1, 2, minus 1, minus 3, 3 in R3. And how about the second one? Let's just do two of them. This is just going to be x cube minus 8x square plus 4x, x cube minus 2x square plus 3x minus 1, x cube minus 2x plus 3. This is in P3 of R. Okay, so we need to check whether the first vector can be written as a linear combination of the other two vectors. Let's look for whether it can be done. So solution. So we would like to see if, so want a comma b in the field of scalars such that minus 2, 2, 2 is equal to a times 1, 2, minus 1. Maybe I should just change this. This makes it, no, this is not going to make it easy. Plus b times minus 3, 3. Yeah, so let's see if we can do that or want to check. Let me just reword what I want. Want to check for the existence of a comma b in R such that this happens. Okay, so let's write it down. Let's write down what this means. What is the right hand side here? The right hand side just tells us that this is equal to a plus minus 3b, which is a minus 3b. This is 2a minus 3b and minus of a plus 3b. So what we want is a solution for the system of equations, which is written down here, 2 and minus of a plus 3b is equal to 2. Okay, so what can we say from here? A minus 3b is equal to minus 2. These two directly implies a minus 2 is equal to 2, which implies a is equal to 4, and this implies 2 times 4 minus 3b is equal to 2. Oh, sorry, 8 minus 3b is equal to 2, which implies b is equal to minus of 6 by minus 3, which is 2. And is it consistent here? We have minus of 4 plus 3 into 2 is 6, which is equal to 2. Yes, so yes. So my claim is, so a equal to 4, b equal to 2 will satisfy the relevant equations that has been written down. So let's see. So hence, easy to check that minus 2 to 2 is equal to 4 times 1 2 minus 1 plus 2 times minus 3 minus 3 3. So yes, therefore we can write the first vector as a linear combination of the other two in R3. Okay, how about the next one? Okay, so let me write this down here. So this is 2. So let's now see what 2 is. 2 was x cube minus 8x, 8x square plus 4x, x cube minus 2x square plus 3x minus 1, and x cube minus 2x plus 3. This in P3 of R, all polynomials of degree less than or equal to 3. Okay, so if we can indeed do that, so want to check if there exists a comma b in R such that x cube minus 8x square plus 4x is equal to a times x cube minus x square, I am sorry, x square plus 3x minus 1 plus b times x cube minus 2x plus 3. But what does this mean? This means what is the right hand side? This is equal to a plus b times x cube plus minus of 2a times x square plus 3a minus 2b times x plus 3b minus a. So this is exactly what the right hand side is going to be. So we would like to see if there exists a and b such that the right hand side is equal to the left hand side here. Okay, so what does this imply? By equating the coefficients of the monomials involved, we have a plus b is equal to 1, minus of 2a is equal to minus of 8, 3a minus 2b is equal to 4, 3b minus a is equal to 0. Okay, so let's see. This implies, so let's see, the second equation minus 2a is equal to minus 8 implies a is equal to minus of 8 by minus 2, which is equal to 4, and a plus b is equal to 1 implies b is equal to 1 minus 4, which is equal to minus 3. Now let's see if the final two, so this 2 implies this. Let's see if the next two equations are consistent. If it is not, then we do not have a linear combination, right? So basically with a equal to 4 and b equal to minus 3, let's look for whether the third and the fourth equation are satisfied. Okay, so what is this going to be? This is just going to be 4 into 3, 12, minus 2 into minus 3, which is 6, which is equal to 18, which is not equal to 4. So there cannot be a consistent choice of a and b which satisfies all these equations. So we don't even need to bother about whether the fourth equation can be satisfied. So the first two equation forces a to be 4 and b to be minus 3, but with 4 and minus 3 the third equation cannot be satisfied. Hence there does not exist a comma b in R such that, well, the first let me put it this way, such that star is satisfied. Okay, so we have checked for one case where the first vector could be written down as a linear combination of the other two, and another in which the first vector cannot be written down as a linear combination of the other two. Okay, so the next problem involves the span. So let me call it problem 5. Yes. So let S1, S2 be subsets of a vector space V. Prove that span of S1 intersected with S2 is contained in the span of S1 intersected with span of S2. Moreover, give an example. When 1 span of S1 intersected with S2 is equal to span of S1 intersected with span of S2, and 2 when the span of S1 intersected with S2 is a strict subset of span of S1 intersected with span of S2. So the problem not only demands us to prove some statement, it also asks us to come up with an example. This is one of the cases where you will have to sit down, look at various examples you have already seen, look for examples of the span and see whether the conditions are being satisfied or not. So this is a good problem for you to think about the various vector spaces that you have already seen. So this is an interesting problem in that sense. Okay, so let's look at a solution. So we need to check for the span of S1 intersected with S2 being a subset of span of S1 intersected with span of S2. So let's take, how do we go about proving such a statement? We take some arbitrary element in the left and prove that it is also necessarily an element in the right. But here it's quite straightforward. So let V be in span of S1 intersected with S2. What does it mean for a vector V to be in the span of some S1 intersected with S2? That means that there exists some V1, V2 up to Vk in S1 intersected with S2 such that V is a linear combination of V1, V2 up to Vk. i.e. there exists V1 to Vk in S1 intersected with S2 and A1 to Ak scalars such that V is equal to A1 V1 plus A2 V2 plus up to Ak Vk. Okay, and what is our goal? Our goal is to show that V is in the span of S1 intersected with span of S2. Okay, so what does it mean to say that V1, V2 up to Vk belongs to S1 intersected with S2? This implies in particular that V1 to Vk belongs to S1 as well. It belongs to both S1 and S2. That is what it means for it to be in the intersection. So in particular it belongs to S1, and since span of S1 is going to consist of all linear combinations of the vectors in S1, this implies A1 V1 plus up to Ak Vk belongs to the span of S1. By a very similar argument though, this is by a similar argument, instead of S1 if you had just picked S2, you would have got that a1 v1 plus a2 v2 up to ak vk belongs to span of S2 as well. So in particular it belongs to both span of S1 and span of S2, and therefore it belongs to the intersection. So we used two aspects here. The one I am underlining in green was because V is in the span of S1, span of S1 intersected with S2, and therefore there exists some A1, A2 up to AK such that V is a linear combination of V1 to Vk. And the one I am underlining in green right now follows because every linear combination of V1, V2 up to Vk which are in S1 should also be in the span of S1. So both the aspects are being used to establish this proof. But that's precisely what we wanted, right? In fact, we have established the proof is the point. So this vector which I have just underlined is the vector V. So this implies V is in span of S1 intersected with span of S2. So we take any arbitrary vector in span of S1 intersected with S2, that will be in span of S1 intersected with span of S2. Therefore, or rather hence, span of S1 intersected with S2 is contained in span of S1 intersected with span of S2. Okay, so now we have proved one part. So we have established this part. So what is left is to give examples of when span of S1 intersected with S2 is equal to the span of S1 intersected with span of S2 and one when it is not equal. So I will not go too much into it. Let me just give you the examples straight away and let me leave it for you to check that if. So the first case where it is equal, let me just take the simple vector space that can come to, that we can consider, which is say R2. Or maybe R3. In R3, consider S1 to be say the vector 1 0 0 0 1 0 and 1 1 0. So this is our S1. And what about S2? S2 is 0 1 0 1 1 0, well 1 2 0. So you should check that, well, span of, what is S1 intersected with S2? S1 intersected with S2 is equal to 0 1 0 1 1 0. And what is the span of S1 intersected with S2? This will be all linear combinations of the vectors written to the right, and you should check that this is the set of all x, y, z in R3 such that z is equal to 0. In fact, you should check that span of S1 is also, so let me call this W, is also equal to W, which is the same as span of S2. So yes, so this is a case where all three are equal, and therefore span of S1 intersected with S2 is equal to span of S1 intersected with span of S2. How about the second case? Yeah, actually we could have also arranged for a case where all the three are not equal, and still we have this, but I will leave that as a thing to think about for you. This is just, after all, picking the right vectors. You should pick various choices and see how it works out. How about the second one? So let me just give you an example and leave the rest to you. We would like to get hold of an S1 and S2 such that span of S1 intersected with S2 is a strict subset of span of S1 and span of S2. That's not difficult. Well, we just take, let's do this. Let's look at in R2, let S1 be equal to the vectors E1, E2, which is 1, 0, 0, 1. And S2 be the set 1, 1, 1, minus 1. And let me leave it for you to check that span of S1 is equal to span of S2 is equal to R2. By now you know that this is a basis, right? And therefore the intersection is also R2. But what is S1 intersected with S2? This is empty. And span of S1 intersected with S2 is just the span of the empty set, which is the 0 subspace. So yes, this is a clear case where it is a proper subspace, or rather it is a subspace which is not equal to span of S1 intersected with span of S2. Okay, the next problem demands that we check whether a particular set is linearly independent or not. So problem 6. Check whether the following set what is the set here? The set here is 1 1 0 0 0 0 0 0 1 1 0 0 0 0 0 0 1 1 1 1 1 0 0 0 0 0 0 1 1 1. So check whether this following set S is linearly dependent in, which is the vector space? This is in the vector space of all 3 cross 2 matrices over R. Okay, so solution. So what do we need to do to check whether a given set is linearly independent or not? We should check for whether there exists a linear combination of it which is equal to 0. Okay, so suppose there is a linear combination. So let A1, A2, okay, we would like to check whether S is linearly dependent or independent. Either way, we want to check for the existence. The existence of what? The existence of scalars A1, A2, how many are there? 1, 2, 3, 4, 5. A1, A2, A3 up to A5 in the field of scalars such that the linear combination A1 times 1, 1, 0, 0, 0, 0 plus A2 times 0, 0, 1, 1, 0, 0 plus A3 times 0, 0, 0, 0, 1, 1 plus A4 times 0, 0, 0, 0, 1, 0, 1, 0, 1, 0 plus A5 times 0, 0, 0, 1, 1, 0 is okay, right? What is the 0 vector here? Remember that the vector space that we are talking about is the vector space of all 3 cross 2 vectors, 3 cross 2 matrices over R, and the 0 vector there is the 0 matrix which consists of the 0 as its entries. So this is just the 0 vector which is 0, 0, 0, 0, 0, 0. This is precisely what we would like to check, whether there exists A1, A2, A3, A4, A5 such that this linear combination is the 0 vector. Okay, so if we are to translate it using the vector addition and the scalar multiplication that is involved in M3 cross 2 of R, which is basically component wise in both the cases. So this is just going to be, let me write down the answer directly. This is going to be A1 plus A4, A1 plus A5, this is A2 plus A4, A2 plus A5, A3 plus A4, A3 plus A5. This is the matrix to the left after doing the calculations, and this we are demanding to be equal to the 0 vector in the vector space of 3 cross 2 matrices over R. So, this is what the demand is. But what does that mean? This means that component wise they are equal. That means A1 plus A4 is 0, A2 plus A4 is 0, A3 plus A4 is 0, and the 3 implies that A1 is equal to A2 is equal to A3. And how about the other one? A1 plus A5 is equal to 0, and this also tells us that A4 is equal to minus of A1, whatever the value of that is. This is also A2 plus A5 equal to 0, A3 plus A5 equal to 0, which implies that A1 is equal to A2 is equal to A3 again, so which is consistent, and A5 is equal to minus of A1. So, in particular, if A1 is equal to 1, then A1, A2, A3 are all 1, A4 is minus 1, and A5 is also minus 1. So, then what do we have? Then let us check for 1, 1, 0, 0, 0, 0 plus 0, 0, 1, 1, 0, 0 plus 0, 0, 0, 0, 1, 1 plus minus 1 times 1, 1, 1, 0, 0, 0, or rather 1, 0, 1, 0, 1, 0 plus minus 1 times 0, 1, 0, 1, 0, 1. This will just turn out to be the 0 vector, which is 2, and therefore this set is linearly dependent. Hence, S is linearly dependent. The next problem demands that we check for a subset to be linearly independent. So, this is problem 7. So, let S be a set of non-zero polynomials in P of R. Let us do one thing, let us put it as a finite set. Let S be a finite set. I do not need to impose this, you should think about why this is true when it is not imposed. The finiteness condition is not imposed. This should still be true, but nevertheless, let S be a finite set of non-zero polynomials in P of R such that no two polynomials have the same degree. So, if one polynomial is a x square plus 1, then the other polynomials, none of them can have degree 2, because x square plus 1 is already having degree 2. So, all the polynomials have distinct degrees. If at all there is a polynomial of say degree 2, there will be only one polynomial which has degree 2. So, they have distinct degrees, okay. So, no two of them have the same degree. Then prove that S is linearly independent. So, as much as the problem might sound sophisticated, it is actually quite simple to prove if you make the right observations. So, let us give a proof or a solution to this problem. So, we know that S is a finite set which has distinct degrees, right. So, what we will do is we will pick the polynomial in S which has the least degree. So, let P1 be the polynomial in S with least degree. Let us say it is D1. P2 similarly be the polynomial which has least degree, however greater than D1. We know that least degree is D1. So, let P2 be the polynomial in S with degree with degree d2 with the least degree, let's call this degree, yeah, degree, let's call the degree, let degree of p1 be equal to d1. So d2, so degree, least degree greater than d1. So there will be only one such polynomial, and let degree of p2 be equal to d2. So notice that d1 is less than d2 and so on. So pick pk. So therefore after finitely many steps, after finitely many such steps in the above algorithmic process, we have S is equal to P1, P2 up to say Pk. There are finitely many of them, such that degree of Pi is equal to Di and D1 is less than, D2 is less than, D2, D3 less than dot 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 dk. So Pk has the highest degree and Pk minus 1 has degree less than the degree of Pk and so on. Okay, now we are almost done. Suppose A1 P1 plus A2 P2 plus up to AK Pk is equal to 0. Then what do we know? Let me ask you what the degree, so let this be equal to Q. So check what will be the coefficient of x to the power dk will be equal, check that this is equal to ak, because a1, a2 up to ak minus 1 do not have x to the power dk in its polynomial expression, because all of them have degree less than dk. Only pk has the monomial x to the power dk, and therefore the coefficient of pk would be ak times the, so okay, so I have to be a bit more careful, times the coefficient of x to the power dk in pk, which is a non-zero number. So let's do one thing, let's call it bk, where bk is equal to the coefficient of x to the power dk in pk of x. But we know that we are looking at this being equal to the 0 polynomial. By hence equating the coefficients, this implies that ak bk is equal to 0. But we know that bk is not equal to 0. Why? Because pk has degree x to the power pk has degree dk, and therefore if its coefficient is 0, then we cannot have its degree to be equal to dk, right? This implies ak is equal to 0. Why? Let me just note down the reason. Since bk is not equal to 0, or rather since bk equal to 0 implies that degree of pk is not equal to dk. But we know that degree of pk is equal to dk, and therefore bk cannot be 0, and therefore ak has to be necessarily 0. Okay, so let's get back to our star. We have just established that ak is 0. This implies that a1 p1 plus a2 p2 plus up to ak minus 1 pk minus 1, this is equal to the 0 polynomial. Because ak is 0, the last polynomial does not contribute. But by a similar argument, we can conclude that ak minus 1 is also equal to 0, and so on. And by a similar argument, now once ak minus 1 is 0, inductively we can say that now a1, a2 up to, by repeating the process above, not inductive, let me just say repeating the above process. We have a1 or rather ak equal to ak minus 1 equal to up to a1 equal to 0. But that's precisely what we wanted to prove. If you notice, if there is a linear combination of p1, p2 up to pk equal to 0, we have just established that the coefficients are necessarily 0. This implies that S is linearly independent. So the next problem is about proving whether a given subset is a basis of the given vector space. So this is problem 8. So determine whether the following subsets or following sets are bases for the vector space or subspace W of R such that 2a plus b plus c is equal to say 0. So where is this a subspace? A subspace W in P2 of R. So we are okay. So what are the sets? Let's see. The first set is S, which is given by x square minus 2 x square minus 2x or rather plus 2x minus 3 2 S is equal to 3x square minus 2x minus 1. So this is 2a plus b minus c. So S is equal to 3x square minus 2x minus 4 x square minus x minus 1 2x square or rather minus 2x square plus x minus 2 4 plus 3, and third one would be S to be say x square minus 2 minus 2x square plus x plus 3. Let's take these three. Okay, so we need to check whether the following subsets are bases of W. What was W? Let me just put W in your view. W is the set of all those polynomials in P2 of R whose coefficients satisfy some relation. So what do we need to check whether something is indeed a basis of W? We need to check that first condition is to see whether it is linearly independent, and the second condition would be to check whether they span our given set. Alright, so let's do that. So solution. So the first problem, let's do both. Let S be x square minus 2 x square plus 2x minus 3. So linear independent. So let a comma b be scalars such that a times x square minus 2 plus b times x square plus 2x minus 3 is equal to 0, the 0 polynomial. So that would imply a plus b times x square plus 2bx plus minus of 2a minus of 3b is equal to 0. But what does it mean to say that a polynomial is 0? All its coefficients are 0. This implies 2b is equal to 0 and hence b is equal to 0. And the first one, a plus b is equal to 0, implies a is also equal to 0, which is inconsistent with minus of 2a plus minus of 3b equal to 0. So yes, this forces a and b to be equal to 0. Hence, S is linearly independent. Yes, so the first thing to note, which I just skipped, is to check whether S is a subset of W. X square minus 2, if you notice, x square minus 2 will just satisfy 2a plus b plus c should be 0. So 2 minus 2 is 0, yes, and 2a is 2, 2 plus 2 minus 3, yeah, so this is a problem, this cannot be in. Oh no, this is bad. 2 plus 2, 4 minus, so this should have been something like minus 4 or something. So let me just do one thing, let me tweak it so that I gain what I want. So it has to be 4. Notice that if it is not 4, that vector will not be in W. So let me come down and slightly change everything. Well, I would like to have that this particular vector is in W, because otherwise we can straight away say that these vectors are not even in W and hence it cannot be a basis. But yeah, so at least let's make it a little more challenging by taking two vectors in W and checking for whether it is a basis. So yes, this is now in this case, let's check once more. X square plus 2x minus 4 will satisfy 2 plus 2 plus minus 4, which is 0. Yes, so this is a subset of W, and this argument which wouldn't have been which is not disturbed at all. So let's go back once more and check line by line. Suppose you have a linear combination which is equal to 0, and grouping for the coefficients, we get a plus b is 0, 2b is 0, minus of 2a minus 4b is 0, or rather a plus 2b is 0. But all the first two forces both a and b to be 0, and it is consistent with the third. Therefore, a and b are forced to be 0. Therefore, S is a linearly independent set. But we are only halfway through. We have just shown that S is a linearly independent subset of W. And the question is whether S is a basis. So, we have to check for whether it is a spanning set. Let me not check brute force that this is a spanning set. I would rather use an indirect argument to conclude that it is a spanning set. So, if S is, so what is the meaning of S being linearly independent? That means that dimension of W is greater than or equal to 2. Why is that the case? That is because every linearly independent set is contained in a basis, and therefore S being linearly independent means that there exists a basis of W which contains S, and therefore it should have at least size 2. So, dimension of W should be greater than or equal to 2. If S is not a spanning set, so if S is not a spanning set, then there exists some polynomial P in capital W such that P is not in span of, what were the two polynomials, or span of S, let me just call it S, span of S, right, that is what it means. And therefore, S union P is linearly independent, and that would imply that dimension of W is at least 3. But it cannot be more than 3, because P2 of R has dimension 3, which is equal to the dimension of P2 of R. And what do we know about subspaces of P2 of R which has dimension equal to 3? It has to be necessarily equal to P2 of R. This implies that W is equal to P2 of R. But this is a contradiction. Why is this a contradiction? Because every element in P2 of R does not satisfy the equation of the coefficients, which I am now underlining in green. For example, you look at 2x square. 2x square has coefficients 2 for x square and 0 and 0. So, the 2a plus b plus c will give us 4, which is not equal to 0. So, P2 of R, every element of P2 of R does not satisfy this relation when it comes to coefficients. And therefore, what was our assumption? So, we proved this problem, which apparently looked very numerical, by a contradiction argument. So, what was the, so if S is not a spanning set, this was the assumption we started off with, and we arrived at a contradiction. And therefore, hence S is a spanning set. That means S is both a spanning set and a linearly independent set, which implies that S is a basis of W. Alright, so we now have, we can conclude something more. This means that the dimension of W is equal to 2. Dimension of W is equal to 2. Okay, good. Because if you look at 2, so I have just underlined in green, S is a subset of, I hope it is a subset of W. So notice that S has 3 elements from W, and we know that dimension of W is equal to 2, and therefore you take any subset of W which has more than 2 elements, it should necessarily be linearly dependent, right? By one of the consequences. So let me say this: S cannot be linearly independent, since by one of the consequences of the replacement theorem, the size of any linearly independent subset of W should be less than or equal to, or let me write it like this, cannot be greater than the dimension of W. And S has 3 elements, which is more than the dimension of W, and therefore S is not a basis. Okay, so now let us come to problem number 3. Problem number 3 has 2 vectors, x square minus 2 and minus 2x square plus x plus 3, minus 2x square minus 4 plus 1 plus 3 is 0. Yes. So, this is a subset of S which consists of 2 vectors. We would like to see whether it is a basis. Again, by one of the consequences of replacement theorem, it is enough to check whether a subset of W of size 2 is linearly independent, or rather let me put it this way. To check that S is a basis of W, it is enough to check for either linear independence or the spanning property. So, let me note what I just said. By a corollary to the replacement theorem, to check whether S is a basis, it is enough to check for linear independence. And why is that the case? Because since S has dimension of W equal to 2 elements. So, if this set is linearly independent, it is necessarily a spanning set. We could have done the other way also. We could have just checked for spanning property, and any spanning set which has a dimension of W elements should necessarily be linearly independent as well. We will just check for linear independence. What was the set S? S was x square minus 2 minus 2x square plus x plus 3. And the check for linear independence is straightforward. If a times x square minus 2 plus b times minus 2x square plus x plus 3 is equal to 0, this would imply a minus 2b times x square plus bx plus 3b minus 2a is equal to 0. And from this we have a minus 2b is equal to 0, b is equal to 0, 3b minus 2a is equal to 0. The second equation already tells us that b is equal to 0, and along with the second equation, both first or third, which is consistent, tells us that a is equal to 0 and b is equal to 0. Therefore, we have established that it is linearly independent, and therefore it's automatically a spanning set, and which makes it into a basis of W. So the next problem demands that we determine what is the dimension of our given subspaces. Okay, so the problem 9. For a fixed scalar A, or rather C, for the fixed scalar C, let W be the set of all polynomials in Pn of R such that P of C is equal to 0. Check that this is a subspace. Here, subspace of Pn of R. Find or determine the dimension of W. Okay, so let's look at a solution. So of course, one needs to check that W is indeed a subspace. Even though it is being said that it is a subspace, it's our job to check that that is a subspace, because otherwise there is no question of finding the dimension. But yeah, so let's as of now let me leave that as an exercise for you to check that it is indeed a subspace. Our goal in this problem, however, is to determine the dimension of W. Okay, so what is W precisely? W is the set of all polynomials such that P vanishes at C. So we know from our basic algebra, we know that if P of C is equal to 0, then P of x is what? This is going to be x minus C times Q of x, where degree of Q of x is degree of P of x minus 1. So this is exactly what our P of x will look like. So in particular, if Q of x, you look at any polynomial of the type x minus C times Q of x, that will satisfy the condition that it vanishes at C. So it's if and only if in some sense. So P of C is 0. We know that, let me put it this way, P of C is 0 if and only if this is the case. So if you look at Q of x varying over all polynomials with say degree 1 to degree 0 to n minus 1. So this is Pn of R, which is up to degree n. So in particular, if Q of x is any polynomial up to degree n minus 1, we should be able to get hold of this. So that gives us a natural candidate. So let me put as a claim, S be equal to 1 times x minus c, which is x minus c, x times x minus c, x square times x minus c, x to the power n minus 1 times x minus c. This is a potential candidate, is a basis of W. So I just described the motivation to guess or conjecture that this particular set will be a basis. So the fact that S is linearly independent follows from one of the problems we have just proved, that S is linearly independent from, let's see, which problem was it? Problem 7. What is that? Problem 7 said that if there is a subset S which consists of polynomials which have different degrees, no two of them have the same degrees, then they should be linearly independent. So notice that we could have done this. The same argument goes through in Pn of R as well. So let me write it. I think problem 7, right? So problem 7. Why? Because this has degree 1, this is degree 2, this is degree 3, and this is degree n. All these have different degrees. So they are necessarily linearly independent. And what is the size of n? So that means dimension of W linearly independent where? In W. So all these are vectors in W and they are linearly independent. Therefore, dimension of W should be greater than, how many of them are there? This is 0, 1, 2 up to n minus 1. So there are n of them, greater than or equal to n. So if dimension of W is not equal to n, if dimension of W is greater than n, it has to be n plus 1, right? Because Pn of R has dimension n plus 1. This would imply dimension of W will be equal to n plus 1, which is equal to the dimension of Pn of R. We have used this type of an argument as well earlier in one of the problems. That would imply W is equal to Pn of R. The only subspace of Pn of R which has dimension equal to n plus 1 is itself. But that cannot happen because this is a contradiction. Because what was our W? W was the collection of all those polynomials which vanishes at C. So in particular, if you look at the constant polynomial 1 at C is equal to 1, which is not equal to 0. Right? The constant polynomial, non-zero constant polynomials do not vanish at any point, and W should necessarily vanish at, every element in W should necessarily vanish at C. Vanish at C, I mean P of C is equal to 0. So this is a contradiction which implies dimension of W. So this assumption which I just underlined cannot happen. This implies dimension of W is equal to n. But what do we have? We have now S, which is equal to, we already have just proved that dimension of S is equal to, dimension of W is equal to n, which is what our goal was. So also notice that S is indeed a spanning set, right? So yes, this is our solution to the problem.